Right, a regular pentagon, OABCD, and we're given some vectors. OA is P and OD is Q, and then K is the number such that DB is equal to KOA. So I'm going to add that on as well. So essentially this is going to be KP. Now we're asked to write down AC in terms of P, Q, and K. I'm just going to draw that on. And we can see it's essentially what KP is to P, this red vector is to Q. And so the answer is simply going to be AC is equal to K lots of Q. In the next part, it says show that CD is equal to minus P minus 1 over KQ. So when I did this, first of all, I was just sort of thinking, well, I want to get from C to D. So what I can do is I can go minus KQ and then minus P and then plus Q. So I could factorize that out as 1 minus K times Q minus P. Now that's all well and good, but it doesn't get me this minus 1 over K. So I need a different approach, but that is actually going to be useful. Like after when I'd done that, I thought actually it's going to be useful because the next part says to find the value of K. So I'm going to potentially create an equation. And here's something we could do instead. We've got we've been using dB and OA and also now AC and OD. Well, let's think about what is equivalent for CD, and it's this vector here. Okay, this vector is going to be K times CD. And from this, I can see that somehow I might be able to divide by that and get a 1 over K. So BO is equal to 1, sorry, not 1 over K, is equal to K times CD. But it is also equal to, remember, we're trying to get from B to O. So we could go minus KP, then minus Q. And that means that I can divide through by K to get CD. CD will then equal minus P minus 1 over K Q. And that's what we wanted. So it just takes a little bit thinking outside the box, using this idea that you have to go along K lots of CD and actually work out what that would be using this B to D and D to O. And after that, we can work out CD by dividing through by K. So that's a crucial result. Of course, if we didn't get it, we can still then use this bit in part C. It's not the end of the world. So therefore, 1 minus K times Q minus P must equal minus P minus 1 over K Q. So these cancel, and we must have 1 minus K is equal to minus 1 over K. If we times through by K, I get K minus K squared is equal to minus 1. And I got myself a quadratic. Of course, K is going to have to be positive because it's going in the same direction, so we can eliminate the negative if we get one. So K squared minus K minus 1 is equal to 0. K is equal to 1 plus or minus 1 minus 4 times minus 1. That's going to be plus 4 all over 2, which will give me 1 plus root 5 over 2. Reject 1 minus root 5 over 2. since less than 0. And hence we've found the value of k. This leads nicely to part D, which is consider triangle DBC or otherwise, find the exact value of sine 54. That's pretty cool. Without a calculator, we're going to get the exact value of sine 54. Sine 30 and so on you would have seen, but sine 54 seems a bit next level, but here we go. Here we are with it. Well, I'm going to draw this triangle in. And remember that in a pentagon, well, it's going to be the number of sides minus 2 times 180 divided by 5 to get each angle. And I can divide by 10 and then times by 2. It's going to be 3 times 36, which is going to be 108. Of course, you could also work out the exterior angle and then do 180 minus that. That's going to be 108, which means if I draw a line coming down, I'll create a right angle triangle and an angle of 54. Now we're on to something. So I'm going to let the magnitude of Q equal the magnitude of P and just be 1. And therefore this length here will be 1. And therefore the magnitude of D to B, remember it was K times Q, and we've just worked out K, it's going to be 1 plus root 5 over 2. So if I call this point M, then D to M is going to be 1 plus root 5 over 4. And that's all we need, because then we can write down that sine 54 is going to be the opposite of our hypotenuse. It's going to be 1 plus root 5 over 4 divided by 1, which is just 1 plus root 5 over 4. And we've managed to find it. So that's a really neat way of proving that result. Almost worth trying to remember this question to, because actually there's another way to do it. And I think it is using a pentagon. I always forget what it is, to be honest. It involves creating a quadratic, which of course we ended up doing here. So maybe it is equivalent, but yeah, this seems really neat anyway.